In lesson 56, we connected a joystick to two Pico W ADCs. Now, Pico ADCs are 16-bit converters, so they convert analog inputs between 0 and 3.3 volts to digital values between 0 and 65,535, or 2 to the 16th counts. Paul's assignment was to create a more intuitive output by scaling the ADC output to report values between -100 and +100 as the joystick is moved from left to right, with 0 reported in the center. Similarly, we should report +100 and -100 as the joystick is moved up and down. The challenge in lesson 57 was to report joystick position as degrees around the center of the joystick. In lesson 58, Paul asked us to convert joystick position to servo position while respecting the fact that our servos can only move between 0 and 180 degrees. And finally, in lesson 59, we were challenged to use the joystick to select colors from the edge of the HSV wheel and display that color on the NeoPixel strip. I expanded Paul's specs a wee bit by adding a second servo. One servo will follow the joystick x-axis position, the other will follow the y-axis position. I also added the joystick push button to the logic to control the HSV value parameter so I could adjust the brightness of the LED strip. And I added the OLED display to display the movement of the joystick. The assignment from lesson 56 requires us to convert the raw X and Y ADC values into values between -100 and +100. This is a straight line conversion, much like we've done in previous lessons. I'll offer a brief explanation for those who haven't seen this before. Those of you familiar with this topic can use the chapter markers below the video to jump ahead. We're often required to convert sensor or user input data from its default scale to some other scale. Thankfully, this can usually be done with a straight line conversion. The sensor data or user input data is often referred to as the independent variable. We'll plot the independent variable on the x-axis of a simple XY graph. The result of the rescaling is often referred to as the dependent variable. We'll plot the dependent variable on the y-axis of our graph. But what to plot? As we move the joystick from right to left, the x-axis plot delivers a voltage from 0 to 3.3 volts to the analog to digital converter. The ADC converts the applied voltage into a count from 0 for 0 volts or fully right to 65,535 for 3.3 volts or fully left. The ADC counts are our independent variable, so we plot the range of possible count values, 0 to 65,535, on the x-axis. As we move the joystick from right to left, we're required to report values from +100 to -100. This is our dependent variable, so we'll plot the range of possible values on the y-axis. At this point, there are two things we know for sure. When the joystick is fully right, the ADC outputs 0, and we want to report that as +100. So that data point is 0, 100. When the joystick is fully left, the ADC outputs 65,535, and we want to report that as -100. So that data point is 65,535 -100. We plot these data points as shown below and connect the points with a straight line. The equation of a straight line is y equals mx plus b, where m is the slope of the line and b is the y-intercept. Given 2 points on the line, m can be calculated as y2 minus y1 divided by x2 minus x1. B can then be calculated as y2 minus m times x2. In lesson 56, we calculate m and b as shown here. We use the same approach to convert scaled x and y values to servo duty cycles in lesson 58 and OLED coordinates for our blit animation. Let's have a look at the code. In this assignment, we start by loading frame buff so that we can blit an image onto the OLED. We load ADC because we're using the joystick as well as pin and I2C. We load math so that we can manage our degree calculations, and NeoPixel because we're using the NeoPixel strip for the lesson 59 part of this assignment. We're using the OLED and we may sleep, so we also import SSD 1306_I2C and time. Next we declare the pins we're going to use for the NeoPixel strip, the OLED, the two servos, the joystick push button, and the joystick pots. Here we configure the OLED display as we've done in past assignments. Here we declare the X-axis and Y-axis servo objects and the joystick ADC objects. Here we declare the NeoPixel object. Pressing the joystick push button steps the HSV values parameter through a range of values from 0 to 1. This function is the ISR, or interrupt service routine, for the push button. Here we declare the joystick push button and the interrupt request for that push button. Here we declare the routine that converts hue, saturation, and value parameters into the RGB values required by the NeoPixel strip in lesson 59. See the lesson 52, 53, 54 homework for a full explanation of this routine. Here we declare the initial values for the various variables as described in the comments. Here we calculate the slope and y-intercept values required for each of the straight line conversions in the program. This section of the code reads the bubble image data into the frame variable, and before entering the while true loop, we clear the OLED, we display the assignment title, and initialize the previous button release variable that's used in the push button ISR. In the while true loop, we start by clearing the right side of the top of the OLED display and the entire blue area of the OLED. Next, we read the X and Y ADC values for the joystick. As required in lesson 56, we scale those raw ADC values to values between -100 and +100. The if statements remove some of the noise around the center zeros. As required in lesson 57, we convert the scaled joystick positions into degrees using the ATAN2 function. The ATAN2 function reports angles beyond 180 degrees as negative angles. Whenever this happens, we add 360 to give us a more familiar result. In lesson 58, we convert the scaled joystick positions into X and Y servo duty cycle values. In lesson 59, we fill the entire NeoPixel strip with the color selected by the degrees variable. The joystick push button will cycle the HSV value parameter from 1 to 0 and back again in steps of 0.2. In the last section of the program, we scale the already scaled joystick position to fit on the OLED. We then blit the bubble image onto the OLED. We finish by drawing horizontal and vertical lines through the center of the blue area. We show the new OLED data, sleep for 0.1 seconds, and repeat the loop. And here's what it looks like. Here you can see the bubble on the OLED follows the joystick position up, down, left, and right. The joystick degrees are displayed in the upper right-hand corner of the OLED. You can also see the X-axis servo following the joystick's left and right motion, as the Y-axis servo follows the joystick's up and down motion. And the NeoPixel strip color changes as we sweep through 0 to 359 degrees. And the HSV value parameter changes when we press the joystick push button. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.